today would be a technology without a compressor. Now this is very interesting. We are saying that we are discussing a technology without a compressor, and we know from our experience that there doesn't exist a technology without a compressor. So before starting a discussion of what this technology is, let us try to understand the role of compressor in the refrigeration system. So the role of compressor in the refrigeration system, as you know, is to maintain the pressure difference between the two heat exchangers. So what are the two heat exchangers in the conventional technology? So in the conventional, that is in the compression technology, vapor compression system, what we do is that we compress the refrigerant from the low pressure, that is the suction pressure, up to the discharge pressure, that is the condenser pressure, by using a compressor. So this compression phenomena is necessary to maintain two different pressures, low pressure in the evaporator and high pressure in the condenser. Now why do we require a low pressure in the evaporator and why do we require a high pressure in the condenser? The reason is we are using a single working fluid in the refrigeration system, and this same working fluid we want it to boil at one temperature and condense at other temperature. So that is the requirement, because we are operating the system in a cycle, a thermodynamic cycle. We want the working fluid, which is the refrigerant, to boil at a low temperature, that is to evaporate at a low temperature, and we want the same refrigerant to condense at the high temperature. And why is that necessary? This is necessary because we want to absorb the heat from the space to be cooled at a low temperature, and we want to reject the heat to the surroundings at a high temperature, and this we need to do by utilizing the latent heat of vaporization and condensation respectively. So this is very clear to us that the role of the compressor is to maintain the pressure difference between the evaporator and condenser. So if you want to understand what is a vapor absorption system, we would be drawing the three components which are already familiar to us when we have studied the vapor compression technology. So which are the three components which are familiar to us excluding the compressor? So these components are, I'm experiencing certain difficulty in drawing straight lines here, but let me try. Okay. So the high pressure side is the condenser. So the box which is drawn above, that I will call it as a condenser. Okay. So let me call this as a condenser. So this is a condenser. This is a condenser which is high pressure heat exchanger, and we can draw similar heat exchanger on a lower side and we'll call it as a evaporator. Okay. So let us say that this is another heat exchanger which is to be maintained at a lower pressure, and it will utilize the phenomena of evaporation for absorbing the heat. So the heat which is absorbed is, let us say, QE dot, and the heat which is rejected, let us say it is QC dot. Okay, and we know that there is an expansion device which maintain the pressure difference between the condensate and the refrigerant entering the evaporator. So this we have studied when we studied the conventional compression system, and we know that on this side, that is at the outlet of the evaporator, the refrigerant flows into the compressor, and the compressor would maintain the pressure difference between. So this is the conventional technology. Let us say this is your compressor. Let us say this is your compressor. A refrigerant enters the compressor. We all know this at a lower pressure, and this compressor would take it to the higher pressure. So this compressor does a very important job of compressing the refrigerant from a high pressure, so from a low pressure, that is the suction pressure, to the discharge pressure. And for this we need to supply certain work in the form of compressor work. And we have studied that this system is the vapor compression technology. Vapor compression technology. Okay. And this system, because it is driven by work, it is called as a work operated system. Work operated system. Okay. And we all know that performance of such a system, work operated system, is captured by the expression of coefficient of performance, COP, which is nothing but the refrigerating effect, which is in my case it is QE dot upon the work input, so W dot. Okay, so this is the vapor compression refrigeration technology. Now what we are saying is that we are replacing the compressor, okay, with a certain set of components, and that technology is called as a vapor absorption technology. So what is done is, so let us first write down what is the inlet to this compressor. It is low pressure vapor entering the compressor, and what is exiting the compressor is the high pressure vapor, which is entering the condenser. Okay, so we want now a technology which would replace this. Okay, we don't want to use compressor, but we don't want to use this, but we want to achieve the same effect. That is, by using certain set of components, this low pressure vapor has to be pressurized to a high pressure vapor. Okay, so that technology is the vapor absorption technology. Now how is that done? You must have figured out that we are calling it as the absorption technology, so it must be related to a phenomena of absorption. Okay, so what is this phenomena of absorption? I'm using American English, so I'm dropping the term U, but you can also spell it as VAPOUR. Okay, so vapor absorption system, as I said, what is this technology? So instead of using the compressor, the three components remain the same. That is, you would have a heat exchanger here. Let me modify the same diagram. I would be rubbing this, and instead of using a compressor, I would be replacing this compressor with three components. And then if I do this, and if I achieve this low pressure vapor, if I'm able to convert it to high pressure vapor, then that technology would be called as the vapor absorption technology. Now what are the three components? And this will become very interesting to you as you would understand that how this compressor is replaced. Okay, once you listen to this, you would understand that this is very logical and well thought idea. In fact, you would imagine that why you or me had not thought of it earlier. Okay, so let us think of this technology. What is it? So what we are going to do now, we are going to replace the compressor, but still we would be achieving the same effect. That is, we would be converting the low pressure vapor to a high pressure vapor. Okay, so in this box now, which I have drawn, I would be replacing the three components. So what are those three components? So one of it is called as the absorber. Okay, so I would be using some another ink now. So that would be called as an absorber. So first is, okay, first is absorber, absorber. The second component is a pump, and if you can think of the opposite of absorber, I will call it as desorber. Desorber. Okay, we'll discuss this. What are they? But just to make sure that you understand that what is absorption technology. So in this absorption technology, we have replaced the compressor with three components, namely an absorber, followed by a pump, followed by a desorber, Okay. So before drawing the actual schematic, let us try to concentrate our attention on these three components. Okay. So what is going to enter, looking at the schematic, what is going to enter the absorber? So what would be entering the absorber would be a low pressure vapor of the refrigerant. So low pressure vapor of the refrigerant enters the absorber, and as the name indicates, it would be absorbed in this. So in this absorber, there is a fluid called as absorbent. So now you understand that along with the important fluid, which is the refrigerant, we also have another fluid in the absorption system, which is called as the absorbent. Okay. So this absorbent, how this absorbent should be? What should be the property of this absorbent? This absorbent should absorb the low pressure vapor and convert it into a solution, convert it into a liquid. Okay, solution. So what we will be getting over here is, we'll be getting here a solution, and because this solution is formed similar to what happens in a condenser in a way, the heat would be rejected. So this heat has to be rejected by an absorber, and the low pressure vapor absorbs. Low pressure vapors are absorbed into the absorbent in the place which is called as the absorber. So absorber is a heat exchanger containing absorbent, and the low pressure vapor, they enter into this absorber and they are absorbed by the absorbent, and we get a low pressure solution. Obviously we are not changing the pressure, so the pressure would be the low pressure of the solution. Now we are familiar with this second component, which is a pump. Okay, it's a liquid pump. So this liquid pump, what happens to this solution in the liquid pump is, this solution is pumped up to the high pressure. So this pump, you know that pump has to be supplied with certain electricity. So let us say that it is WP, and this pump would pump this solution from a low pressure to a high pressure. So what you get at the outlet, at the exit of the pump, is a high pressure solution. Okay, high pressure solution. This high pressure solution then enters into a component which is called as a desorber. So because we are familiar with English language, that opposite has to do with the opposite effect. So absorber absorbs, and desorber would perform the function of desorption. That is, it would release the refrigerant vapor. Okay, so absorber absorbs the refrigerant vapor, low pressure vapor, and the desorber would release the high pressure vapor. So this, you are getting the high pressure vapor now. Okay, so the high pressure vapor is now released by the desorber. Okay, and the liquid solution, the remaining solution, we'll use a term called as weak solution and strong solution. I will define that shortly, but now for the time being, just remember that it is a weak solution which is going to come back. Okay, come back into the it has to be expanded, throttle into the desorber. Okay, so there has to be a throttling device here, and this would be throttle into the absorber back again. So this weak solution returns back to the absorber, right? And this liquid vapor would again be further absorbed in the absorber. Again we get a strong solution. This strong solution would be pumped to a high pressure. So this way, now look at these three components and let us think how they are replacing the compressor. So what does the compressor do in the conventional technology? In the mechanical compression system, the compressor takes the low pressure vapor and converts it into high pressure vapor. Okay, so if we look at this as a system which I had drawn, a system comprising of absorber, pump and desorber. So what does this system in total do? This system in total would absorb the low pressure vapor and it would reject the high pressure vapor. So this has achieved, this combination of absorber, pump and desorber has achieved the same effect as that of the compressor, right? And this technology is called as the vapor absorption technology. Okay, now one would wonder as to how this technology helps. Okay, then why are we complicating the matters? For example, we had a beautiful compressor in the conventional VCR technology, and now we are saying that this vapor absorption technology, VAR, vapor absorption technology, has a complicated thing. It has got an absorber, it has got a pump, and it has got a desorber. Okay, so what is the advantage of this? So let us discuss the advantage. The advantage, now let us first compare the two. Compression technology, vapor compression system, and the absorption technology, the vapor absorption system. I would be using simply these two terms to distinguish between the two. Okay, constructional wise, let us talk about the two. So this is VCR and this is V absorption system, VAS. Okay, so compression system has got a compressor and vapor absorption system does not have a compressor. But what it has instead of a compressor, it has got three components, three major components. One is the absorber, second is the absorber, followed by a pump, and followed by a desorber. Mind well that desorber is also called as vapor generator. Now I'm using the British English and hence I'm including this term U. Okay, vapor generator. So what are the three components of absorption system? Absorber, pump and vapor generator. Okay, now what does the compressor do? It would convert the low pressure vapor to high pressure vapor. What this three would do? It would convert the low pressure to a high pressure system. What is the fluid which is used in the vapor compression system? It is the refrigerant which is used in the vapor compression system, which performs the role of refrigeration. That is, it would take the heat from a low temperature heat exchanger, that is evaporator, and cool the space, and it would reject the heat via the high temperature heat exchanger, that is condenser, and reject the heat to the surroundings. Similarly, in the same way, absorption system also has a refrigerant and it would perform the same role, right? However, in addition to the refrigerant, we have seen that the absorption system also has a absorbent. Okay, and what is the role of the absorbent? The role of the absorbent is to absorb the refrigerant and convert that refrigerant to a solution, so that it can be pumped, right? One would wonder that whether electricity is required for this. Obviously, electricity would be required for this. In absorption system also we require electricity. Why do we require electricity? We require electricity in order to operate a pump. Okay. Why do we require electricity here? We require electricity here in compression system to operate a compressor. Now, in addition to electricity, what do we require in an absorption system? Now, if you look at the diagram, I didn't explain that, but this desorber, I said that absorber, the heat has to be rejected, and in order to release this high pressure vapor from a solution, the high pressure solution enters the desorber, we need to supply certain heat, which is QG. Okay, G is for vapor generator. So desorber is also called as vapor generator. So in order to see that the high pressure vapors are released from the solution, this desorber needs a heat input in the form of Qg. And then if you don't supply heat input to this machine, then we won't get this vapors released. Okay. So in addition to the work, you would see that along with the electricity, we also require the heat input to this machine. Now one might wonder, what is the advantage then of this vapor absorption system? Okay, you see, if you look at this comparison, this has got one component for compression, and for compression this system has got three components, that is absorber, pump and desorber. It has got one fluid, that is a refrigerant. Instead of one fluid, you see that this system has got two fluids, one is the refrigerant and the other is the absorbent. Compression technology has got one input, that is electricity, and then this absorption technology has got two inputs, that is it has got electricity also to be supplied and heat is also to be supplied. Now what is the advantage then of using this system? So for that, to understand the advantage, we need to revise the thermodynamic concepts which we have learned. How do you figure out what is the electricity required for the compressor? So if you want to calculate the electricity required for the compressor in the VCR technology, how do you calculate the electricity required for the compressor? Electricity required for the compressor is an open system, and we can model it as a steady flow system. So for a steady flow system, the work input, just a minute, for a steady flow system, the work input is given by m dot into v dot into delta p, where v is the specific volume. Okay, so if I want to calculate the work input, I guess there are some network issues. Okay, so if I want to calculate the work input of this compressor, work input of the compressor is given by V into delta P. Delta P is what? Condenser pressure minus the evaporator pressure. V into delta P, condenser pressure minus the evaporator pressure. And if you want to calculate the pump work is also equal to V into delta P, that is V into condenser pressure minus evaporator pressure. Now if you assume two systems to be operating between the same two pressures, that is same condenser pressure and same evaporator pressure, which work input would be more? One might think that the work input is the same. However, if you ponder over the fact that this fluid which is entering the compressor is a gas, whereas this fluid which is entering the pump is a liquid, we can straight away say, because this Vg has got to be very, very large, Vg has got to be very, very large than Vf, we can safely say that the work input of the compressor is too much. Okay, so the work required for compressor is too high as compared to the work required for pumping, and that is advantage. What is the advantage of using a vapor absorption system? Vapor absorption system requires less of electricity for a similar capacity system as compared to a compression technology. In other words, the major input for this vapor absorption system is the heat input which is necessary at the generator level. Okay, so what we require at the absorption technology, the major input for driving this refrigeration phenomena is the heat input, whereas for the compression technology, the input required for refrigeration is the electricity. So high grade energy, which is electricity, is used for vapor compression system, whereas the low grade energy, which is the heat, is used for absorption technology, and that is the advantage of absorption technology. So in real life, wherever we have source of waste heat available, let us say for example we have waste heat in the flue gases of the engine, diesel engine or diesel generator, or you have heat in the form of solar energy trapped by concentrators, or we have, let us say, some steam in a sugar factory or a dairy industry generated from the boiler, and you have some excess steam there, we can harness this technology economically. Okay, so the viability, which system to choose, whether one should go for a vapor compression technology or whether one should go for a vapor absorption technology, depends upon number of factors, but the major reason would be the economical reason. Vapor compression technology, because the components are smaller and the pressures are also relatively lower, they are cheaper. The lower initial cost is the significance of vapor compression technology. We need to invest less money for same capacity, whereas in absorption system, the initial cost or the capital cost is more. That is, we need to put in a larger amount of money for running the vapor absorption system. Okay, we need to borrow more capital as compared to a vapor compression system if you are talking about similar tonnage capacity, right? However, the running cost of vapor absorption system at times could be less, especially when the electricity becomes costlier, or especially when we have a scenario where we can tap waste heat resources, waste heat energy, or we can tap the solar energy economically. One would find that vapor absorption system would have a lower running cost. That is, the fuel cost would be less, okay, as compared to the electricity cost which is required for vapor compression system. Okay, so we cannot simply say that this is best or this is not best. We find by experience that in most of the places, vapor compression system is widely used because of the obvious advantages of lower initial cost and higher coefficient of performance, whereas vapor absorption system does have a market. If you do a Google search and if you look for the absorption chillers which are being manufactured, you will find that they are also commercially available, they are also widely used, and they are also used in places where we have waste heat energy. Okay, so both these are mature technologies and both have a unique market, a niche market for them, and both are viable technologies in their own areas, right? So this is a brief introduction of vapor absorption system. We would go into the analysis, we would go into the practical systems, we would go into how do you calculate the performance of the system in more detail in the next class. I will be sharing this practical which is to be performed on the vapor absorption system in the next video on your WhatsApp groups. Okay, you can go through that and convince yourselves that such a kind of systems does exist. We have a beautiful system in our lab, okay, and we do conduct very interesting experiments on that. In the real life, we have huge systems of hundreds of tons refrigeration effect in the market, which you can do a Google search out of interest and find out which are the major players in the market which do supply the commercial absorption chillers. We'll stop for now. Bye. Thank you very much.